So we have what's called a vector space, and we already know a bunch of vector spaces. They're just these sets of vectors that we're familiar with: R2, R3, R sub n, or R sup n. And these are sets of vectors that have very nice properties. And there are other vector spaces that aren't these generic ones that we use a lot. But a subspace is some subset of a vector space that still has some of these nice properties. So a subspace of a vector space is a set of vectors that has three properties. So the first one is the zero vector is in the subspace. So if you have a subspace, you have to have the zero vector as part of that set. Second, you have to have what's called closure with vector addition. So we'll say the subspace is closed with respect to vector addition. So what does that mean, closure? It means if I pick any two vectors, say u and v, inside of a vector space, we'll call the vector space H. So if I pick any two vectors that are already in the vector space, then when I add them together, that new vector is also in the vector space. So you can't add two vectors and get a vector that's outside of the subspace. And the same thing is true for scalar multiplication. So we'll say the subspace is closed with respect to scalar multiplication. So what does it mean to be closed with scalar multiplication? If we pick a scalar, say s, and we pick a u that's inside the subspace, then if we multiply that scalar times u, that new vector will still be in the subspace. So again, you can't multiply a vector in the subspace by a scalar and get a vector that's outside of the subspace. So it turns out that if you span any set of vectors, you automatically get a subspace. So anytime we've talked about spanning any set of vectors, we have created subspaces. So let's just check that. So we'll say let S be the span of a set of vectors. So we'll call it U1, U2, up to U sub n. So we want to know, is S a subspace? So the span is all linear combinations. So let's say if I pick a vector x in S, that means that x is some linear combination of these vectors. So let's check to see if the three things are satisfied, the three properties. So one is the zero vector part of S. So is the zero vector a part of S? So the question is yes, because if I just let all these C's be zero, then when I take the linear combination, I get the zero vector. And the span is all linear combinations. So that zero's got to be one of those. So 0 is 0u1 plus 0u2 all the way up to 0u sub n. So that checks out. That satisfies that property. The zero vector is inside S. Next, what about vector addition? So if, let's say, x and y are in S, is x plus y in S. So let's just say x is this vector c1 u1 plus c2 u2 plus c sub n u sub n, and then y, it's also in S, so it's got different coefficients, but the vectors are the same. So if I take x plus y and I add these together, right, I can add up these as I go and combine them up. So if I add these two, I get C1 plus D1 times U1 and C2 plus D2 times U2 and so forth till I get to the end. Cn plus D sub n times U sub n. And if C and D are constants, then C plus D is just another constant. So these are just scalars. And S is all linear combinations of these vectors, and this is just one of those linear combinations. So this also has to be in S. So that means that's satisfied. All right, what about scalar multiplication? If I multiply S times X, what do I get? Well, that's S times C1, U1 plus S times C2, U2, and so forth until I get to the end, S times C sub n, U sub n. And these S times C's are just two constants multiplied together. You multiply two constants together, you get another constant. So these are just scalars. So, and again, the span of the vectors is all linear combinations of those vectors. So this has to be an S as well. So this one's satisfied as well. So any span of a set of vectors is automatically a subspace. So the column space is a subspace, and it is we use this notation, column space of a matrix A is the set of all linear combinations of the columns of A. So since it's a set of all linear combinations of the columns of A, it's the span of the columns of A. If it's the span of the columns of A, then it's a subspace. So the column space of A is a subspace. So let's do an example. We have matrix A and vector B is B in the column space of A. So what we're asking is, can we write B as a linear combination of the columns of A? So I'll say A2 or A1, A2, and A3 are the columns of A. So basically, does this system have a solution? Can I find a C1, C2, and C3 that'll give me B? So I just have to augment A with B, row reduce it, and see if the system has a solution. Don't really care what the solution is. We can find it pretty easily. We just want to know, is there a solution? So if you row reduce this, I used a calculator, and I got this. This is a system that's consistent. It does have a free variable. Your variables are C1, C2, and C3. C3 is free, but there is at least one solution. So there's infinitely many. So the answer is yes. We can write B as a linear combination of the columns of A. So what is one of those combinations? Well, C3 is free, so what if we let C3 be 0? Then C2 would be -5/2. C1 would be -9/2, and that would be your linear combination. -9/2 A1 minus 5/2 A2 plus 0 A3 would get you B. So you should try that. You should multiply first column of A times -9/2, second column of A times -5/2, add them together, see if you get B. So another space that we like is the null space. So the null space is it's the null space of a matrix A. So we use this notation: null A is the set of all solutions to the system AX equals 0, to the homogeneous system. So we already know that 0 is a part of this, right? And if you span the 0 vector, you get the 0 vector. If you get free variables, remember in the homogeneous system, if you get free variables, your solution is the span of a set of vectors. So that makes the null space a subspace. So this is also a subspace. We talked about, if this was a line or a plane in R2 or R3, and this extends further, but if you have free variables, then you can span those your solution, and that creates a subspace. So if it's a span of a set of vectors, then it's a subspace. So let's do an example of this guy. I have the same two A and B. I've got matrix A, vector B. Is B in the null space? Well, what you're asking is B one of the solutions to AX equals 0? So can I plug in B here for X and it solved the equation? So all I have to do here is to multiply A times B and see if I get the 0 vector. So instead of augmenting and row reducing, I'm going to multiply them. So let's do the first row dotted with this column. So I get 3, -9, so that's -6, and 16. So I get 10 here. That's not 0. So I'm done. I know the answer to this is no. This B is not one of the solutions to AX equals 0, so it's not in the null space. It's not a vector that maps to 0. So a basis of a subspace is, we'll say a basis is a linearly independent set of vectors that span the subspace. So we talked about sets of vectors that are linearly independent. we've talked about sets of vectors that span a vector space. A basis is a linearly independent set of vectors that span a subspace together. So they have both properties. They're linearly independent and they span the subspace. So that's called a basis. It's kind of like the minimum number of vectors, the minimum vectors you need to generate a subspace. So let's find a basis for the column space and the null space. And I have this matrix. And to find the basis for the column space, I know that the columns of A already span the column space because that's what the column space is. It's the span of these vectors. So that's already taken care of. So what I need to do now is figure out which one of these are independent. I know that they're not all independent from each other because I've got too many vectors. So which ones are independent? The vectors that are independent will form our basis of the column space. So I need to row reduce. Really, I need to augment with 0. So let's augment this with 0. Row reduce it. And I used a calculator here. Wait, this is 0. So this row reduces to this matrix. And I've only got two leading ones, only have two pivot columns. So the pivot columns tell you which columns of your matrix will give you a basis for the column space. So we can say basis for the column space is the set of vectors that just contains these two vectors, the first column of A and the third column. They're the ones that are independent from each other. All the other ones, all the other vectors, we can write as a linear combination of the first and third. So really, to span the same space, we only need these two vectors. We actually didn't need all 5 of these. So the span of column A1 and column A2 is actually the same as the span of all 5 columns. And all of that's equal to the column space. So what that tells you is your basis kind of pairs everything down, and this is the minimum number of vectors that you need to get the same space. So these two vectors generate the whole column space, and we didn't need all of those vectors. So what about the null space? Well, the null space are all the solutions to ax equals 0. So we need to find these x's. And we've already augmented this with 0 and row reduced it. So this should be easy to do. So let's say x1 is positive 2x2 plus x4 minus 3x5, right? Got our variables here, x1, x2, x3, x4, x5. x2 is free. x3 is negative 2x4 plus 2x5. x4 is free. x5 is free. So we need to write the solutions here in parametric vector form. So x is, we're going to have an x2 vector, going to have an x4 vector, and we're going to have an x5 vector. So I'm going to go through and pick out all the x2 things out of the solution, all the x4s, and then all the x5s. So this is the span of these three vectors because the solution is any linear combination of these three vectors. We can plug in anything we want for x2, x4, and x5. So it turns out that when you solve this system this way, these vectors are automatically linearly independent. So if they're independent and they span the null space, then that means they make a basis. So the basis for our null space is going to be just the set that contains these three vectors. I don't care what you call the set, but a basis is a set of vectors. So if you're asked to write a basis, you got to write it in a set. Okay. So you got to use these brackets and put them inside the brackets, separate them with a comma. So let's do this again. This matrix is already row reduced. So my pivot columns are the first, second, and fifth columns. So my basis for the column space are just these three. And then for the null space, I've got to solve the equation bx equals 0. Right, so I'm looking for the solutions to this equation. So I'm going to pretend that this is augmented with 0 and solve it. So x1 is, looks like 3x3 minus 5x4. x2 is negative 2x3 plus x4. x3 is free. x4 is free. x5, remember it's augmented with 0 here. Looks like x5 is just equal to 0. Okay. So I need to write this in parametric vector form. I'm going to have an x3 vector and an x4 vector. And I'm just going to write down all the things that have x3s. Now I'll write everything that has an x4. These two vectors are independent. They span the null space because these are the solutions to all the they're all the solutions to bx equals 0. So it's different linear combinations of these two vectors. So basis for the null space here is just the set that has these two vectors inside.